Hello everyone, I'm Mark Daniel Kara. This time, we are going to talk about the Coanda effect and its application in real life. Is the tendency of a fluid jet to stay attached to a convex surface. It is named after Romanian inventor Henry Coanda, who described it as the tendency of a jet of fluid emerging from an orifice to follow an adjacent flat or curved surface and to entrain fluid from the surroundings so that a region of lower pressure develops. This phenomena happens because of the fast-moving fluid like air. The rushing stream of air pulls the air around it. It is because the fast-moving air has a lower pressure, therefore attracting the surrounding slow-moving air, low pressure. The movement of the pressure is from high to low. Example is when you cover a candle with a cylinder and blowing it on its surface perpendicular to the candle. The air seems to change direction and tends to follow the shape of the cylinder blowing the candle off. As we can see, as air rushes against the cylinder, the direction of the flow is being separated. While the air is following the shape of the cylinder, the air around it is being pulled. As soon as the rushing air reaches the rear part of the cylinder, it continues to pull the air around it. This part tends to have a very few surrounding air to pull, causing this part to have a low pressure. Now, the surrounding air on this side has a greater amount of pressure, therefore pushing the stream of rushing air towards the part of the cylinder with a lower amount of pressure, making it follow the shape of the cylinder. In application to real life, we use Coanda effect to produce lift on an airplane's wings and helicopter's blades. Here is an example. This is an airfoil, a cross-section view of an airplane's wing. Based on the simulation I have done on SolidWorks, we can see here that the air is coming from this direction. As soon as the air hits the leading edge, the air slowed down and the direction separated, the other goes up and the other one goes down. Focusing at the top part of the wing, we can see that, like the cylinder candle experiment, the air tends to follow the shape of the wing. The rushing air follows the front part up to the trailing edge. It is because that this part causes a low pressure wherein there is less air to pull, allowing the surround air to push the direction towards the wing's shape. Now the direction of the air here is pointing downwards. Looking at the lower section, as soon as the air changed direction, the shape of the lower section guides the air towards the ground, slightly slowing the air's velocity. In the simulation, we can see how pressure changes depending on the shape of the surface. The pressure on the upper section is obviously lower because of the angle of the surface. This is because the air here is more disturbed compared to the lower section. We can see that in this part, there is a minimal drop of pressure, but majority of this part has a higher pressure. In this case, the higher pressure portion tends to push towards the lower pressure portion, therefore generating lifts.